you're falling. Not through air, but through space itself. Time stretches around you like taffy while your body elongates, atoms ripping apart molecule by molecule. Ahead lies absolute darkness, a boundary where the universe simply stops making sense. This is what happens when you cross the event horizon of a black hole. And somewhere out there, right now, millions of these cosmic predators are hunting. Black holes aren't just strange astronomical objects. They're places where reality breaks down completely, where our most fundamental laws of physics throw up their hands in defeat. They're the universe's ultimate mystery and its most violent creation. Over the next 50 minutes, we're going to explore everything about them, from their violent births to their role in destroying entire galaxies. But first, we need to understand how something so impossible could even exist. The story begins not with darkness, but with light. Stars are massive. Our sun weighs roughly 2 billion tons. Every second, it converts 4 million tons of matter into pure energy through nuclear fusion. That's 4 million tons simply ceasing to exist, transformed into the light that makes life on Earth possible. The outward pressure from this continuous thermonuclear explosion is the only thing preventing our sun from collapsing under its own gravity. Now imagine a star 50 times more massive than our sun. The core burns hotter, brighter, faster, churning through its fuel at an incomprehensible rate. Where our sun will shine for 10 billion years, these stellar giants exhaust themselves in just a few million. They're sprinting toward an inevitable deadline. Inside the core, fusion creates heavier and heavier elements. Hydrogen becomes helium. Helium fuses into carbon. Carbon into oxygen, neon, magnesium, silicon. Each step releasing less energy than the last. The star is building its own coffin, layer by layer, like an onion made of different elements. Each shell burns at millions of degrees, but the progression is relentless. Then the core starts making iron. Iron is the end of the line. Fusing iron consumes more energy than it releases. For the first time in the star's life, the core stops generating outward pressure. And without that pressure, there's nothing to hold back the crushing weight of the layers above. What happens next takes less than a second. The core collapses. Atoms are crushed together so violently that electrons are forced into protons, creating neutrons. The entire core, a mass greater than our sun, compresses into a ball maybe 20 kilometers across. Then it rebounds. The outer layers, still falling inward, slam into this rebounding core at a quarter of the speed of light. The collision releases more energy in 1 instant than our sun will produce in its entire 10 billion year lifetime. The star explodes outward in a supernova so bright it can briefly outshine an entire galaxy of 400 billion stars. But that's just the fireworks. The real story is what's left behind. If the original star was massive enough, somewhere above 25 solar masses, even neutron pressure can't stop the collapse. The core keeps compressing. Neutrons are crushed together, then crushed further. Density climbs past anything that should be physically possible. And then something genuinely bizarre happens. The escape velocity exceeds the speed of light. Think about throwing a ball upward. If you throw it hard enough, it'll escape Earth's gravity and drift into space forever. That's escape velocity, about 11 kilometers per second for Earth. For the Sun, it's 600 kilometers per second. But as this stellar core collapses, its escape velocity keeps increasing. At some critical point, it crosses 300,000 kilometers per second. The speed of light. Nothing can move faster than light. Not matter, not energy, not information itself. So when the escape velocity exceeds this cosmic speed limit, nothing can escape. Not particles, not radiation, not even light itself. A black hole is born. The boundary where this happens, where escape velocity equals light speed, is called the event horizon. Cross it, and you're not coming back. Ever. The laws of physics won't allow it. You could fire the most powerful rocket ever conceived, and it wouldn't matter. You could harness the energy output of an entire star, and it still wouldn't be enough. Once you're inside, all paths lead inward. But here's what really twists your mind. From the outside, you'd never actually see someone cross the event horizon. As they fell closer, time dilation would make their clock run slower and slower relative to yours. They'd appear to freeze at the boundary, their image growing dimmer and redder as the light they emit gets stretched into longer and longer wavelengths. To them, they'd cross in finite time. To you, watching from a safe distance, they'd take forever. They'd be gone, but their image would remain, a ghost frozen at the moment of their disappearance. The event horizon isn't even the strangest part. What lies at the singularity breaks the laws of physics itself. But we'll get to that. Right now, we need to talk about what black holes actually look like. You've probably seen the images, the famous orange ring around a black shadow, photographed by the Event Horizon Telescope in 2019. That wasn't just a picture. It was a triumph of human ingenuity that required turning the entire Earth into one massive telescope. The black circle in the center isn't the event horizon itself. It's larger, called the photon sphere. This is where light can orbit the black hole in circles. Some of those photons spiral inward and vanish. Others escape, creating a shadow roughly 2.5 times wider than the event horizon itself. The orange ring. That's superheated matter, spiraling inward at significant fractions of light speed, heated to billions of degrees through friction and compression. This accretion disk glows across the electromagnetic spectrum. Radio waves, visible light, X-rays, gamma rays. Some of this matter doesn't fall in. Instead, it gets channeled along magnetic field lines and shot outward in jets, traveling at 99% of light speed, extending for thousands of light years. These jets are so energetic they can sterilize entire regions of galaxies, preventing new stars from forming. But stellar mass black holes, the ones formed from individual dying stars, aren't the real monsters. They're typically between 5 and 100 times the mass of our Sun. Their event horizons range from 15 kilometers to 300 kilometers across. Terrifying, yes, but almost quaint compared to what lurks at the centers of galaxies. Supermassive black holes make stellar mass black holes look like grains of sand next to mountains. At the heart of our Milky Way galaxy sits Sagittarius A star. It weighs 4 million times what our Sun weighs. Its event horizon would fit comfortably inside Mercury's orbit. Every few thousand years, it swallows a star whole. We've watched stars orbit around this invisible monster at speeds exceeding 5,000 kilometers per second. That's fast enough to cross the United States in half a second. And Sagittarius A star is small for a supermassive black hole. The largest we've discovered is TON 618, weighing 66 billion solar masses. Its event horizon is 11 times wider than Neptune's orbit around our Sun. If you replaced our Sun with TON 618, its event horizon would swallow everything out past Uranus. This single object contains more mass than all the stars in some small galaxies combined. How do black holes get this big? We're still figuring that out. They might form from direct collapse of massive gas clouds in the early universe. They might grow by continuously feeding on surrounding matter. They might merge with other black holes, combining their masses in collisions that literally create ripples in space-time itself, gravitational waves that we can now detect billions of light years away. In 2015, we heard 2 black holes collide for the first time. The LIGO detector picked up gravitational waves from 36 and 29 solar mass black holes spiraling together. In the final fraction of a second before merger, they were orbiting each other 250 times per second. The collision converted 3 solar masses, 3 times the mass of our Sun, into pure gravitational wave energy. For that brief instant, the merger released more power than all the stars in the observable universe combined. Let that sink in. 2 objects, each smaller than a city, produced more energy than 400 billion galaxies. Not through light, not through heat, through literally shaking the fabric of space-time itself. And we detected those shakes after they traveled for 1.3 billion years across the expanding universe. Since then, we've detected dozens more mergers. Each one teaches us something new about how black holes behave, how they form, how they grow. We're watching the universe's most extreme physics laboratory in action. But there's something deeply unsettling about black holes beyond their destructive power. They represent boundaries, limits to what we can know. Information that crosses the event horizon is lost to the outside universe forever. Or is it? Stephen Hawking spent decades wrestling with this question, eventually proposing that black holes might not be completely black after all. Quantum mechanics, the physics of the very small, suggests that particle-antiparticle pairs constantly pop into existence throughout empty space, then annihilate each other almost instantly. But near an event horizon, something strange can happen. One particle falls in while its partner escapes. From the outside, it looks like the black hole is emitting radiation. Hawking radiation. This means black holes can evaporate. Slowly. Incredibly slowly. A stellar mass black hole would take longer than the current age of the universe to evaporate. But given enough time, truly incomprehensible stretches of time, even supermassive black holes will eventually decay into nothing, releasing their energy back into the void. Though by then, the universe will be so old and cold that this radiation will be the only thing happening anywhere. We'll explore that apocalyptic timeline later. Right now, we need to understand what happens if you actually fell into one of these things. Because the physics gets genuinely weird. Time doesn't just slow down, it becomes a direction. Space doesn't just curve, it tears. And your body wouldn't just be destroyed, it would be transformed into something that barely resembles matter at all. The journey from the event horizon to the singularity is unlike anything else in physics. It's where Einstein's relativity meets its absolute limit, where the math breaks down and infinity appears in the equations. It's where we have to confront the uncomfortable truth that our most successful theories simply stop working. But before we dive into that nightmare, we need to talk about what black holes do to the space around them, how they warp time itself into impossible geometries, creating regions where cause and effect break down, where the future becomes inevitable and inescapable. Part 2. Imagine you're standing at the edge of a cliff. You lean forward slightly and feel that primal fear, gravity pulling you toward the drop. Now imagine a cliff where leaning forward doesn't matter, where standing completely still doesn't matter, where the ground beneath your feet has already decided you're falling, and nothing in the universe can change that fact. That's what crossing an event horizon feels like. Except the cliff is invisible, and once you've leaned too far, even light itself can't climb back out. The event horizon isn't a physical surface. There's no wall, no barrier, no membrane. It's purely a mathematical boundary, a point of no return written into the geometry of space-time itself. From the outside, it looks like a perfect sphere of absolute darkness. But that darkness isn't an object. It's the absence of information. It's every photon that ever crossed that boundary, now trapped forever in a one-way journey toward the singularity. Here's what makes this truly disturbing. If you watch someone fall toward a black hole, you'd never see them cross the horizon. Time dilation would stretch their image across eternity. They'd appear to slow down, redshift into deeper and deeper wavelengths, their light taking longer and longer to reach you. Eventually they'd fade from view, frozen at the boundary forever. But from their perspective, they'd cross in finite time. They'd feel nothing special at the moment of crossing, just continued freefall. The universe behind them would appear to speed up, blue shifting into higher energies. They'd watch the future of the cosmos unfold in fast forward while plunging toward their doom. Two observers experiencing completely different realities. Both perspectives equally valid. Both absolutely true. That's relativity at its most counterintuitive. But let's focus on the infalling observer, because their experience reveals something profound about how black holes distort reality. As you fall, you'd notice the stars behind you clustering into a shrinking circle. The black hole's gravity is so intense it bends light rays into curved paths. You're not just falling through space, you're falling through space-time itself, and space-time is folding around you like a funnel. The closer you get, the stronger the tidal forces become. We mentioned spaghettification earlier. Here's why it happens. Gravity follows an inverse square law: double the distance, quarter the force. But near a black hole, distances matter enormously. Your feet are slightly closer to the singularity than your head. That difference creates a differential in gravitational pull. For stellar mass black holes, this difference becomes lethal long before you reach the horizon. Your feet would be pulled with thousands of times more force than your head. Your body would stretch, then tear, then atomize into a stream of particles. Interestingly, supermassive black holes are gentler. Their event horizons are so large that the gravity gradient is actually quite shallow at the boundary. You could cross the horizon of Sagittarius A star and survive for minutes, maybe even hours, before tidal forces became significant. You'd have time to contemplate your fate, time to realize that every direction you look now points toward the singularity. Even up leads to the center. The singularity isn't somewhere you're falling toward, it's somewhere in your future. A moment in time you're guaranteed to reach, not a place you can avoid. This is where the physics becomes genuinely alien. Inside the event horizon, the radial direction, the path toward the singularity, becomes time-like. It's no longer a direction in space, it's a direction in time. Moving toward the singularity isn't like moving toward a wall. It's like moving toward next Tuesday. You can't avoid next Tuesday by turning left. You can't avoid the singularity by firing your rockets. The singularity is in your future as inevitably as tomorrow. What's actually there at that point? We genuinely don't know. General relativity predicts infinite density, infinite curvature, a place where the equations themselves break down and produce nonsensical answers. Infinities in physics usually mean we're missing something important. They're red flags, indicating our theories have reached their limits. We need quantum gravity to describe what actually happens at the singularity, and we don't have a complete theory of quantum gravity yet. Some physicists speculate the singularity might be a quantum foam of space-time, fluctuating at the Planck scale. Others suggest it could be a bridge to another region of space-time, a wormhole, though almost certainly not traversable. A few radical theories propose the singularity doesn't exist at all, replaced by some exotic quantum structure we can't yet imagine. But these are educated guesses, mathematical possibilities. Nobody knows. Nobody can know. The event horizon guarantees that information stays trapped forever, or does it? Because Hawking radiation suggests something information does escape, just scrambled beyond recognition. We'll return to that paradox later. For now, consider what black holes do to their surroundings. They don't just sit passively in space. They actively warp everything nearby into impossible configurations. Within a certain distance, about 3 times the radius of the event horizon, light itself can orbit. Photon spheres, circles of light trapped in eternal loops. If you hover just outside this sphere, you could theoretically see the back of your own head as light rays curved completely around the black hole. Closer still, inside the photon sphere but outside the event horizon, lies the ergosphere. Here, space-time itself is dragged around by the black hole's rotation. You couldn't remain stationary even if you fired your rockets at full thrust. The fabric of reality is flowing past you like a river, and you're caught in the current. This region makes possible something remarkable: the Penrose process, a method for extracting energy from a rotating black hole. Drop an object into the ergosphere at the right angle with the right trajectory, let it split in 2, and one piece can escape with more energy than the original object possessed. The black hole loses rotational energy in the process. It's the universe's most efficient power plant, theoretically. No civilization has built one yet, but give it time. These gravitational distortions create observable effects. When a black hole has a companion star, it can pull gas from that star in a process called accretion. The gas doesn't fall straight in. Conservation of angular momentum forces it into a disk, an accretion disk, spinning around the black hole at substantial fractions of light speed. Friction within this disk heats the gas to millions of degrees. It glows in X-rays. It produces jets of particles shooting outward at relativistic speeds, perpendicular to the disk. Some of these jets extend for thousands of light years, visible across the universe. These accretion disks are among the brightest objects in the cosmos. Not the black holes themselves, they remain perfectly dark, but the material spiraling toward them. Quasars, the most luminous objects in the universe, are supermassive black holes actively feeding on surrounding gas. A single quasar can outshine an entire galaxy of 400 billion stars. All that light comes from an accretion disk smaller than our solar system. Think about the energy density involved. All that power, all that radiation, all that violence, concentrated in a region that would fit comfortably between the Sun and Neptune. The temperatures and magnetic fields near these disks are so extreme, they accelerate particles to energies we can barely reproduce in our most powerful colliders. The universe has built particle accelerators that dwarf anything we've constructed. And at the center of nearly every large galaxy, one of these monsters lurks. The Milky Way's black hole is relatively quiet right now. It's not actively feeding. But forensic evidence suggests it had active periods in the past. Gas clouds show signs of having been illuminated by intense radiation about 6 million years ago. Something woke it up briefly. Something fell in and made it flare. Then it went quiet again, like a dragon returning to sleep. Other galaxies aren't so peaceful. Galaxy M87, that same galaxy whose black hole we photographed, has a jet extending 26,000 light-years from its core. Material is being flung outward at 99% of light speed. The energy required to maintain this jet is staggering, equivalent to converting the mass of the Sun into pure energy every 6 months. And M87's black hole has been doing this for millions of years without pause. These supermassive black holes didn't form from stellar collapse. They're too big. A star, no matter how massive, can't produce a billion solar mass black hole when it dies. These monsters grew over time, through mergers and accretion, starting from smaller seeds in the early universe. But here's the puzzle. We've found supermassive black holes in galaxies less than 1 billion years old. That's not enough time for them to grow through normal feeding. They seem to have formed quickly, perhaps from direct collapse of massive gas clouds, perhaps through other mechanisms we haven't identified yet. The relationship between galaxies and their central black holes runs deeper than we initially suspected. The mass of a galaxy's supermassive black hole correlates tightly with properties of the galaxy itself, the velocity of stars in the central bulge, the total stellar mass. It's as if galaxies and black holes grew together, influencing each other's evolution. The black hole represents only about 1/10% of the galaxy's mass, yet somehow these two components know about each other. Jets from the black hole can regulate star formation across the entire galaxy. The black hole, despite being tiny compared to the galaxy, acts like a thermostat controlling the whole system. We're starting to understand that black holes aren't just endpoints of stellar evolution. They're architects of cosmic structure. They shape galaxies. They control star formation. They create the most energetic phenomena in the universe. Without black holes, galaxies would look completely different. The universe would be unrecognizable, but they're also ticking clocks. Hawking radiation means even these titans are temporary. Given enough time, truly astronomical amounts of time, they'll evaporate completely. A black hole the size of a grain of sand would have more mass than Mount Everest. Drop it on Earth, and it wouldn't bounce or roll. It would fall straight through the ground, through bedrock, through the planet's mantle, oscillating back and forth through Earth's core like a pendulum. Each pass consuming more matter, growing larger, until our entire world collapsed inward around it. Within minutes, everything you've ever known would be compressed into an object smaller than a marble. This isn't speculation. This is what happens when matter reaches densities that shouldn't exist. The universe has created objects so dense that a teaspoon of their material would weigh as much as a mountain. But even neutron stars pale compared to what lies beyond. Cross a certain threshold and not even neutron degeneracy pressure can resist. Gravity wins absolutely. The collapse continues past any stopping point, past neutron density, past nuclear density, past anything we can describe with normal physics. The matter doesn't stop at some final compressed state. It keeps going. And that's where reality breaks. At the center of every black hole sits the singularity, not a small object, not a compressed sphere. A point of literally zero volume containing all the black hole's mass, infinite density. Every equation we have produces infinity when you try to describe it. That's not a failure of mathematics. That's physics telling us something fundamental has gone wrong. The singularity represents a boundary where our understanding collapses as completely as the matter that formed it. General relativity predicts singularities, but can't describe what happens there. Quantum mechanics might have something to say, but breaks down under these conditions. We need a theory of quantum gravity to peer into these regions, and we don't have one. String theory offers possibilities. Loop quantum gravity suggests alternatives, but we're essentially blind. The singularity remains hidden behind the event horizon, shielded from observation by the universe's most effective censorship mechanism. Roger Penrose formalized this as cosmic censorship, the hypothesis that singularities can't exist without event horizons. Naked singularities, if they could form, would be visible to the outside universe. We could observe infinity directly, but nature seems to forbid this. Every singularity we know of is clothed by an event horizon. Whether this is an absolute law or just a very strong tendency remains unknown. Physicists have tried to construct scenarios that produce naked singularities. So far, something always prevents it. The universe appears to have a modesty principle. But here's what disturbs physicists most. The singularity isn't just impossibly dense. It's not just a point where equations fail. It represents a genuine edge to space-time itself. Not an edge in space, like the surface of an object. An edge to the fabric of reality. Time itself terminates at the singularity. There's no after, because time stops existing. This isn't like time slowing down near the event horizon. This is time ending as a concept. And if you fall past the event horizon, reaching the singularity becomes inevitable. Not just likely, inevitable. It's as unavoidable as tomorrow. Once you cross that boundary, the singularity isn't somewhere in space you're moving toward. It's a moment in your future you can't escape. Think about what that means. Outside a black hole, you can choose your direction in space. You can move left or right, forward or backward, up or down. Time flows in one direction, but space is yours to navigate. Cross the event horizon, and those properties swap. The singularity becomes a direction in time, not space. Trying to avoid it would be like trying to avoid next Tuesday. You can move around spatially all you want inside the event horizon, but you're still approaching the singularity temporally. Your engine thrust doesn't matter. Your velocity doesn't matter. The singularity is coming in your future as surely as the next second. Some solutions to Einstein's equations suggest rotating black holes might contain something different. The Kerr metric describes a black hole with angular momentum, and its interior structure is bizarre. The singularity isn't a point, but a ring. And through that ring, the mathematics suggests a tunnel to somewhere else. Maybe another region of space-time. Maybe another universe entirely. These are called Einstein-Rosen bridges, more commonly known as wormholes. Before you get excited about shortcuts across the cosmos, there's a problem. Actually, several problems. The wormhole, if it exists, is unstable. It would collapse faster than light could traverse it. You'd need exotic matter with negative energy density to hold it open. We've never found anything like that. And even if you could stabilize it, tidal forces inside would be lethal. The tunnel would likely be narrower than an atomic nucleus. Sending information through would require solving engineering problems that make building a Dyson sphere look trivial by comparison. But the mathematics doesn't care about engineering challenges. The equations say these structures could exist, at least in principle, and that raises profound questions. If black holes are tunnels, where do they lead? Do supermassive black holes contain entire universes? Could our universe itself be the interior of a black hole in some larger cosmos? These aren't idle philosophical musings. They're legitimate questions physicists grapple with, trying to understand what general relativity actually predicts. The interior geometry of a black hole is so counterintuitive that even physicists who work with the equations regularly struggle to visualize it. Space and time trade roles. Directions become times. Futures become places. The normal rules of causality bend into shapes that feel impossible. And we can never verify any of this through observation because nothing comes back out, except perhaps information. This brings us to the black hole information paradox, one of the deepest problems in theoretical physics. Quantum mechanics says information can't be destroyed. It can be scrambled, hidden, spread out. But the total information content of the universe must remain constant. Black holes seem to violate this principle. Throw a book into a black hole and that information appears to vanish. The black hole's mass increases slightly, but all the specific information in the book seems gone forever. Hawking radiation makes this worse. As black holes evaporate, they emit random thermal radiation. Nothing about that radiation encodes what fell in. It's like burning a book and claiming the smoke contains the text. Eventually, the black hole evaporates completely. Where did the information go? Did it genuinely disappear from the universe? That would break quantum mechanics. Or is it somehow encoded in the radiation in ways we don't understand? That would require physics we haven't discovered. This isn't academic hair-splitting. This is a genuine crisis in fundamental physics. Either quantum mechanics is wrong, general relativity is wrong, or we're missing something profound about how reality works. The debate has raged for decades. Hawking initially argued information was destroyed. Later he changed his mind, proposing it might be preserved at the event horizon, encoded in subtle correlations in the radiation. The holographic principle emerged from this. The idea that all the information in a volume of space can be encoded on its boundary surface. String theory offers some solutions. Certain calculations suggest information does escape, carried by subtle quantum correlations in the Hawking radiation. But we're far from consensus. The information paradox remains unresolved, a signpost pointing toward physics beyond our current understanding. Black holes, once again, are nature's way of breaking our theories and demanding better ones. Here's another puzzle. Black holes are the simplest objects in the universe. A black hole is completely described by just 3 numbers: mass, electric charge, and angular momentum. That's it. Every other property of the matter that formed it is erased. A black hole made from collapsing hydrogen looks identical to one made from collapsing iron, assuming the mass, charge, and spin match. This is the no-hair theorem. Black holes have no distinguishing features beyond those 3 parameters. Yet the matter that forms black holes is enormously complex. A collapsing star contains vast amounts of information: the positions and velocities of countless particles, the structure of its magnetic field, chemical composition variations, everything. All of that complexity disappears. The universe goes from a state of high information content to one of minimal information. This seems to violate thermodynamics. Entropy should increase, but erasing information means entropy appears to decrease. Bekenstein and Hawking solved this by showing black holes themselves have entropy, enormous entropy. The entropy of a black hole is proportional to its surface area, measured in Planck units. A solar mass black hole has entropy vastly exceeding all the entropy of all the matter that formed it. The universe's entropy books balance after all. But this raises yet another mystery. What physical degrees of freedom account for this entropy? What microscopic states is the black hole exploring? We don't know. String theory offers some answers for certain special black holes, but a general solution remains elusive. Meanwhile, black holes keep challenging our assumptions. Observations of gravitational waves from merging black holes have revealed populations we didn't predict. Black holes with masses in ranges we thought shouldn't exist, spin rates that constrain formation mechanisms. Some mergers suggest hierarchical growth, black holes that formed from previous black hole mergers. We're watching black hole evolution in real time now, and it's revealing gaps in our models. The universe has had nearly 14 billion years to cook up black holes. From stellar mass to supermassive, from slowly rotating to nearly extremal spin, from isolated to binary to congregating in dense clusters at galaxy centers. They've shaped cosmic structure, they've regulated galaxy formation, and eventually, in the unimaginably distant future, they'll be the last objects remaining before even they evaporate into the void. Part 4, the final act. So imagine this. You're the last conscious observer in a universe gone dark. Trillions upon trillions of years have passed. Every star has died. Galaxies are distant memories, their constituent atoms scattered or consumed. The cosmic microwave background has cooled to near absolute zero, and scattered through this frozen void are the final monuments to matter itself. Black holes, slowly bleeding energy into nothingness through Hawking radiation. This is the black hole era, the final act of cosmic history before eternal darkness. The supermassive black holes, those galactic anchors weighing billions of solar masses, will outlast everything else. A black hole's evaporation time scales with the cube of its mass. Small black holes vanish relatively quickly. A solar mass black hole would take 10 to the 67 years to evaporate. But a billion solar mass supermassive black hole, 10 to the 98 years. Numbers so large they lose meaning. For perspective, the current age of the universe is merely 10 to the 10th years. We're talking timescales a trillion times longer than the universe has currently existed. During most of this incomprehensible duration, black holes just sit there, isolated, cold, emitting Hawking radiation so gradually that their temperature barely registers above absolute zero. A supermassive black hole's event horizon temperature hovers around 1/1000th of a degree Kelvin. The cosmic microwave background is currently warmer, so these giants actually absorb more energy than they emit. They're growing, not shrinking. But eventually, expansion wins. The universe continues expanding. The background radiation continues cooling, and finally drops below even the frigid temperatures of supermassive black holes. That's when the final countdown truly begins. Hawking radiation intensifies as a black hole shrinks. Temperature is inversely proportional to mass. Halve the mass, double the temperature. This creates a runaway process. As the black hole radiates away mass, it gets hotter, which makes it radiate faster, which makes it shrink quicker, which makes it hotter still. The finale is explosive. In its last second of existence, a black hole releases energy equivalent to millions of nuclear bombs. A final flash of light in an otherwise dead cosmos. Then nothing. Just photons and elementary particles dispersing into infinite space. One by one, every black hole in the universe undergoes this fate. The stellar mass ones go first, over timescales of 10 to the 67 years. Then the intermediate mass black holes. Finally, after durations that dwarf even these incomprehensible numbers, the supermassive behemoths at the centers of long-dead galaxies evaporate in their turn. And then, pure emptiness, a universe in true heat death. Just photons and neutrinos, and perhaps some exotic particles, all spreading apart forever as space continues its eternal expansion. Temperature approaches absolute zero. Entropy maximizes. Nothing can ever happen again. black holes were the last holdouts, the final structured objects, and even they couldn't resist the second law of thermodynamics forever. But here's where it gets genuinely strange. Some physicists argue this might not be the end. Roger Penrose proposed conformal cyclic cosmology, the idea that our universe's heat death might be the initial conditions for another Big Bang. When everything has decayed to massless particles, the concepts of time and distance lose meaning. This state might be mathematically identical to an infinitely hot, dense singularity. The end becomes a beginning. Another possibility involves quantum tunneling. Even in the emptiest possible space, quantum field theory predicts vacuum fluctuations. Given infinite time, a fluctuation could nucleate a new universe. Probability doesn't matter when you have eternity. The improbable becomes inevitable. Or perhaps the multiverse theories are correct, and countless other universes exist beyond our cosmic horizon, each with their own black holes, their own timeline toward heat death or renewal. These ideas remain speculation. What we know for certain is that black holes represent finality. They're cosmic garbage disposals, information shredders, one-way tickets to oblivion. Or are they? The information paradox still haunts theoretical physics. If information truly can't be destroyed, then somehow those subtle quantum correlations in Hawking radiation must preserve everything that ever fell in. Every atom of every star, every particle from the early universe that got swept up during cosmic evolution, every hypothetical alien civilization that might have accidentally crossed an event horizon, all of it encoded in the radiation pattern. Extracting that information would require measurements far beyond anything we can imagine. You'd need to capture essentially every single photon emitted over the black hole's entire evaporation lifetime and analyze quantum correlations between them. The technical challenges are absurd, but in principle, the information survives. This suggests something profound. Black holes aren't really destroyers. They're transformers. They take ordered information and scramble it into the most disordered form possible, thermal radiation at a characteristic temperature. But the information persists, just in a form so thoroughly mixed that reconstruction seems practically impossible. Some theorists go further. The holographic principle suggests our entire universe might be like a black hole's event horizon, a lower dimensional surface encoding all the information of the higher dimensional volume. Reality itself might be a hologram, with black holes serving as our best laboratories for testing these ideas. We've journeyed from stellar death to cosmic rebirth, from event horizons to singularities, from spaghettification to galaxy formation, from theoretical puzzles to observational triumphs. Black holes have gone from mathematical curiosities to confirmed reality to precision science. They've taught us that space can trap light, that time is flexible, that gravity isn't a force but geometry, that information and entropy are physical concepts with cosmic implications, that the universe is stranger than we imagined and probably stranger than we can imagine. The supermassive black holes at galaxy centers shaped everything we see. Without them, galaxies would be formless clouds. Stars wouldn't have formed in the patterns they did. Planets wouldn't exist in the configurations we observe. Life might never have emerged. We owe our existence to black holes in a sense, and eventually they'll outlast us. Long after Earth is gone, after the Sun has died, after the Milky Way has merged with Andromeda, and that combined galaxy's stars have all burned out, the black holes will remain. Silent monuments in an empty cosmos. Until finally, even they surrender to quantum mechanics and evaporate away, leaving behind only the faintest whisper of radiation as evidence they ever existed. Black holes are nature's ultimate paradox. The simplest objects with the deepest mysteries. The darkest voids that shine the brightest light on physics. The endpoints of stellar evolution that might be gateways to new universes. They remind us that reality operates by rules we're still learning, that our intuitions fail at extremes of density and gravity, that the universe doesn't care about our comfort or comprehension. It simply is, following mathematical laws that permit phenomena we can barely conceive. We've mapped their shadows. We've heard them collide. We've measured their influence on galaxies and gas and stars. But we still don't truly understand them. The singularity remains hidden. The information paradox persists. Quantum gravity stays elusive. Black holes are questions as much as answers, and perhaps that's fitting. The universe seems designed to keep us curious, to always dangle one more mystery just beyond our grasp. Just when we think we've figured something out, nature reveals another layer of complexity. These cosmic enigmas will continue challenging us for generations. New telescopes will image more black holes in higher resolution. Gravitational wave detectors will catch more mergers, revealing populations we haven't predicted. Theoretical physics will keep wrestling with singularities and information and quantum gravity. And maybe, eventually, we'll understand. We'll have a complete theory of quantum gravity that describes what really happens at the singularity, that resolves the information paradox, that unifies all of physics into one coherent framework. Black holes will finally make complete sense. Or maybe they'll always remain partially mysterious. Maybe there are limits to knowledge, horizons beyond which even information can't return. Maybe some questions don't have answers we're capable of grasping. Either way, black holes stand as the universe's ultimate statement about the nature of reality. They're where physics goes to die and be reborn, where certainty evaporates and possibility explodes, where the journey from star to singularity to radiation completes the cosmos's longest, strangest arc, from light to darkness to light again. That's the black hole story, and ours too. We've spent 50 minutes traveling through cosmic horror and mathematical beauty, from collapsing stars to evaporating remnants in a cold, empty universe. But here's what strikes me most about black holes. They're mirrors. Not literal mirrors, obviously. Light doesn't bounce off them, but they reflect back our deepest questions about existence. What is time? What is space? What happens to information, to memory, to history itself? Black holes force us to confront these questions with no easy answers waiting. Every major revolution in physics has come from taking something seriously that seemed impossible. Newton took falling apples seriously and found universal gravitation. Einstein took the speed of light seriously and found relativity. Hawking took quantum mechanics near event horizons seriously and found that black holes evaporate. The pattern holds. Impossibilities become discoveries when someone bothers to do the math. Right now, somewhere in the universe, two black holes are spiraling toward collision. Their event horizons will touch, merge, settle into a single sphere. In that moment, they'll release more energy than all visible stars combined, and we might detect it. A ripple in space-time reaching across billions of light years, arriving at Earth as a chirp in our detectors lasting a fraction of a second. That's where we are as a species. We've built machines sensitive enough to feel space-time itself vibrate. We've photographed the shadow of an object that shouldn't cast shadows. We've measured things that Einstein himself thought would remain forever beyond measurement. The black holes don't care. They'll keep forming, keep feeding, keep merging, keep evaporating according to laws we're still decoding. They operated for billions of years before humans existed, and they'll continue operating for durations that make billions of years look like eye blinks. But we're here now. Conscious matter, trying to understand the universe that created it. And black holes are the ultimate test of that understanding. They break our physics in the best possible way, by showing us exactly where our theories end and the unknown begins. The singularity hides behind the event horizon. Quantum gravity remains undiscovered. The information paradox persists. These aren't failures, they're invitations. Somewhere, a graduate student is working on equations that might resolve the information paradox. Somewhere, engineers are designing the next generation of gravitational wave detectors that will hear black hole collisions from the universe's first billion years. Somewhere, Theorists are exploring mathematical structures that might describe what actually exists at a singularity. They're all chasing the same thing we've been chasing this entire time: understanding. Not comfort, not certainty. Just a clearer picture of how reality actually works. Even when that reality includes objects so extreme, they seem designed specifically to confuse us. Black holes taught us that gravity isn't a force, but curved space-time. They revealed that space and time are malleable, not fixed. They showed us that information and entropy have physical meaning. They forced quantum mechanics and general relativity into the same equations, creating tensions that still haven't been fully resolved. Every mystery they've presented has made physics deeper, richer, more connected. The search for quantum gravity is unifying theoretical frameworks that seemed completely separate. The holographic principle is changing how we think about reality itself. The information paradox is revealing connections between thermodynamics, quantum mechanics, and space-time geometry that nobody suspected. This is how science advances. Not by finding comfortable answers, but by discovering better questions. Black holes are question generators, and we're only just beginning to ask the right ones. So here's where we actually stand. We've confirmed black holes exist. We've measured their properties. We've detected them colliding. We've photographed their shadows. We've developed mathematical frameworks that describe their behavior with remarkable precision. But we still don't understand them. Not really. Not completely. The journey from John Michel's dark stars in 1783 to the Event Horizon Telescope image in 2019 took over 2 centuries. The journey from here to actually understanding quantum gravity might take another 2 centuries, or longer, or we might crack it tomorrow. Science doesn't follow predictable timelines. What matters is that we keep looking, keep calculating, keep building better detectors and more powerful telescopes and more sophisticated theories. Because black holes aren't going anywhere. They're patient. They'll wait while we figure them out. And when we finally do, when someone writes down the equations that describe what really happens at a singularity, that resolve the information paradox, that unify quantum mechanics and gravity, it won't be the end of the story. It'll be another beginning. Those equations will raise new questions we can't currently imagine, pointing toward mysteries we don't yet know exist. That's the real lesson from black holes. The universe is deeper than we think. Always. Every time we peel back one layer, another appears underneath. The cosmic onion never runs out of layers. Black holes are where stars go to die, and physics goes to be reborn. They're the universe's way of saying, you think you understand gravity? Cute. Try explaining this. And we are. We're trying. We're making progress. The supermassive black hole at the center of our galaxy is sitting there right now. 4 million solar masses compressed into a region smaller than Mercury's orbit. It's not doing much at the moment, just existing, warping space-time around itself, holding the galaxy together through pure gravitational dominance. In a few billion years, when Andromeda collides with the Milky Way, our central black hole will eventually merge with Andromeda's. Another gravitational wave event, this one happening in our cosmic backyard. The resulting black hole will anchor the merged galaxy, shaping its evolution for billions more years, until finally, in the incomprehensibly distant future, even it evaporates. The last gasp of the last supermassive black hole in the observable universe will be a flash of Hawking radiation so far in the future that the numbers become meaningless. But that's not an ending. It's a transformation. Matter to energy, structure to entropy. Information scrambled but preserved. The universe doesn't destroy things. It just keeps changing them into different forms. Maybe that's the real insight. Black holes aren't cosmic villains. They're not destroyers or monsters or voids of pure evil. They're just really extreme physics. The universe playing by its own rules. Rules that happen to permit objects so dense that light can't escape. Those rules also permit stars, planets, life, consciousness, and curiosity. The same physical laws that create black holes created us. We're both children of quantum fields and curved space-time, just expressing those fundamentals in wildly different ways. So when you look up at the night sky, remember, between the visible stars, hiding in the darkness, black holes are out there. Some of them are stellar corpses, quietly existing. Others are actively feeding, powering some of the universe's most energetic phenomena. The supermassive ones anchor their galaxies, shaping cosmic structure on the largest scales. They're all following the same rules, warping space-time, emitting Hawking radiation, preserving information in forms we can barely comprehend, waiting patiently for us to figure them out, and we will. Maybe not completely, maybe not in our lifetimes, but piece by piece, equation by equation, observation by observation, we're getting closer to understanding the universe's strangest objects. The black holes will still be there, doing their thing, regardless of whether we understand them or not. But we're the ones who get to experience the journey from ignorance to knowledge. That's the real privilege. Not the destination, but the process of discovery itself. From star death to Hawking radiation, from event horizons to singularities, from classical physics to quantum gravity, the story of black holes is still being written. And the next chapter, that's being worked on right now in observatories and universities and theoretical physics departments around the world. The universe created objects so extreme they break our best theories. Then it created us to notice them, study them, and eventually understand them. That's the actual miracle. Not that black holes exist, but that we can know they exist and begin to comprehend what they mean. The journey from stellar collapse to heat death spans timescales beyond human conception. But the journey from wondering about dark stars to photographing event horizons took only a few centuries of human effort. We're fast learners, for conscious matter that only recently figured out it's made of atoms. Black holes are the universe's ultimate challenge and its greatest gift. They're problems that demand solutions we haven't invented yet. And in solving them, we'll understand reality itself more deeply. That understanding won't come with a dramatic revelation or a single breakthrough moment. It'll come gradually, through hard work and clever experiments and mathematical insights, building on each other over decades or centuries. But it will come, because that's what humans do. We figure things out. Even when those things are objects so strange that time becomes a direction, space becomes a trap, and the laws of physics themselves break down. Especially then, those are exactly the challenges worth taking on. Black holes showed us that the universe is weirder than we imagined. Now we're learning it's weirder than we can imagine. And somehow, that's not discouraging. It's thrilling. Because it means there's always more to discover, always deeper layers to explore, always new questions waiting just beyond our current understanding. From the first collapsed star to the last evaporated supermassive black hole, the story spans all of time. We're somewhere in the middle of that story, watching, learning, calculating, discovering. The black holes don't know we exist. They don't care. They'll continue being black holes regardless of our theories or observations. But we exist anyway. We care anyway. We build telescopes and detectors and theories anyway. We spend lifetimes trying to understand objects we'll never visit, using mathematics to probe regions we'll never observe directly. That's what makes us remarkable. Not that we're important to the cosmos, we're not. But that we're curious enough to study it anyway, to map the darkness, to shine light on mysteries that will outlast our species by timescales that make our entire existence look like a rounding error. Black holes are where physics goes to extremes. They're laboratories testing the limits of natural law. And they're patient teachers, waiting for us to ask the right questions and do the math carefully enough to find the answers. Some of those answers we have now, others will take generations more work. And some might remain forever just beyond our reach, hidden behind event horizons, or lost in quantum fog, or buried in mathematical complexities we can't yet navigate. But the search itself is worth it. Because understanding black holes means understanding gravity, spacetime, quantum mechanics, information, and entropy at their most fundamental. It means glimpsing the deep structure of reality itself. That glimpse is what we've been building toward this entire time. From the first stars to form after the Big Bang, to the last black holes that will evaporate in the ultimate future, the story is one of transformation. Matter to energy, order to entropy, structure to radiation. But the information persists. The story continues. Nothing is truly lost, just changed beyond recognition. And somewhere in that story is us, briefly aware, frantically curious, desperately trying to understand before our moment passes. We're the universe looking at itself, trying to comprehend its own strangest creations. The black holes will outlast us, but we're the ones who get to know they're there, to measure them, to photograph them, to hear them collide. We're the ones who get to wonder what lies at the singularity and work toward answers. That's enough. That's everything. The journey from question to understanding, from mystery to knowledge, from darkness into light. That's what makes the search for truth about black holes worth every ounce of effort we've poured into it. The universe made black holes. Then it made us to figure them out. Both facts are equally improbable and equally true. And in that improbable truth lies something worth celebrating. Consciousness arising from matter, curiosity emerging from chemistry, understanding growing from ignorance. Black holes represent the ultimate challenge. But we're still here, still looking, still calculating, still trying to understand the universe's deepest secrets, one equation at a time. And that's exactly where we should be.